In this presentation, we shall describe two variance reduction techniques. The first is called antithetic variates, and the second is called common random numbers. Antithetic variates is a variance reduction technique whose objective is to reduce the number of runs or replications needed to achieve the required precision in estimating the true mean. As in common random numbers, the other technique, the reduction in the number of runs is achieved by inducing correlation between runs to reduce the variance of the estimator. Antithetic variates is applicable to simulating a single system. This is in contrast to common random numbers, which is aimed at comparing two or more alternative system configurations. Antithetic variates aims to induce a negative correlation. Again, this is in contrast to common random numbers, which aims to induce positive correlation. Antithetic variates tries to induce a negative correlation by using complementary random numbers to drive the two runs in a pair of simulation runs. For example, if U is a uniformly distributed random variable, from which we sample particular random numbers used for a specific purpose in the first run, that is to generate the ith arrival time, then 1 minus U should be used for the same specific purpose in the second run, that is, again, to generate the ith arrival time. The idea is simple. If the first U results in a long arrival time, then the second should result in a short arrival time. This should produce a better estimate of the average arrival time. Notice that it is valid to use 1 minus U in the second run instead of drawing a fresh random number from the random number generator, because if U is uniformly distributed between 0 and 1, then 1 minus U is also uniformly distributed between 0 and 1. The use of U in the first run and the use of its complement 1 minus U in the paired replication must be synchronized. That is, both random variables must be used for the same purpose. If synchronization is lost, then antithetic variates may backfire and actually increase rather than reduce variance. There are several modeling tricks for keeping random numbers synchronized, and these include the use of dedicated random number streams. For example, we use the same random number stream for arrivals in both runs. Using the inverse transform method of variate generation whenever possible. The reason for this is because the inverse transform method uses exactly one uniformly distributed random number, and that way we can control the use of the numbers provided by the random number generator. Another technique is the appropriate wasting of random numbers to keep the uses of the random numbers synchronized between the two runs. Another common trick is the pre-generation of random variates when we have control of the sequence of random numbers produced before they get mixed up in the simulation process. Finally, advancing the streams of random numbers across multiple replications helps to keep the random numbers synchronized and not reusing the same random number sequences. It must be emphasized that there are no guarantees ahead of time that antithetic variates will indeed work and reduce the variance of the average. A necessary requirement is for the model to have a monotonic response to a particular random number used for a specific purpose. For example, in an MM1 queuing system, a smaller U results in shorter inter-arrival times, which in turn produce more arrivals, which tends to increase the average delay time in queue waiting for service, as well as the average contents of the queue. It is important then that smaller u always increase the average delay in Q. We shall now describe the mathematical basis for antithetic variates. Suppose that we make n pairs of simulation runs, resulting in the pair of observations shown below, where xj with a superscript of 1 is the jth observation from the non-antithetic or standard first run that uses the sequence of random numbers u, and xj with a superscript of 2 is the corresponding jth observation from the antithetic, that is, the second run, that uses 1 minus u. Because both samples xj superscript 1 and xj superscript 2 are observations of the same system, their expected values are equal and equal to mu, that is, the unknown mean of the system production. Similarly, their variances are equal and they equal the unknown variance, again, of the unknown system production. Let xj be the average of the jth pair of standard and antithetic observations. Remember that xj1 and xj2 use u and 1 minus u as the random numbers to produce the output observations xj1 and xj2. If we add those two, xj1 and xj2, and we divide by 2, then we obtain the average of the jth pair. Clearly, the average of the jth pair of observations is an unbiased estimator of mu. This is simple to illustrate. The variance of xj depends on the correlation between the pair of variables being averaged. That is, the variance of xj equals sigma squared over 2 times 1 plus rho j, where sigma squared is the variance of the system and rho j is the correlation between the two observations, xj1 and xj2. If we run multiple replications so that we have n pairwise observations, we can obtain the average of the n pairwise average observations xj. So the average is 1 over n times the sum of the pairwise average of the observations. The expected value of x bar is indeed mu, that is the unknown quantity that we're trying to estimate. Because the x sub j are independent and identically distributed, the variance of the average x bar is equal to sigma squared divided by 2n times 1 plus the correlation coefficient rho sub j. If instead of performing antithetic variate sampling, we simply run the simulation over 2n times or 2n replications and we obtained independent samples, then the variance of their average is again simple to calculate and it would equal sigma squared over 2n. We now have two variance measures that we can compare. One is sigma squared over 2n times 1 plus rho, and the other one is simply sigma squared over 2n. From here we can reach some obvious conclusions. If we compare the two variances, we can see that the effectiveness of antithetic variates depends on rho. If rho is less than 0, that is, if we induce negative correlation in the pair of samples, then the variance of the average is reduced, which is desirable. If rho is 0, that is, we do not induce any correlation between the pair of observations, then the variance stays the same. If rho is positive, then the variance actually increases, which is undesirable. So the objective of antithetic variates is to keep rho negative, and that requires special care in the design of the simulation model. Fortunately, we can standardize the structure of a stroboscope simulation model that uses antithetic variates into a template that can be reused whenever needed. We shall present two such templates. The first one controls the desired number of replications. The second one is controlled by the desired width of the confidence interval for the mean. In the first template, we define a save value and replications with a star followed by a number, which is the desired number of replications. The statement streams2 defines two additional streams other than stream 0. Notice that we will only use stream 0 and stream 1 in the simulation model, and we will leave stream 2 to seed the streams in the next pair of runs. This will become clear later on in the description of the model. The persistent save value, seed save, stores the same seed that is used twice to seed all the streams, one for the standard run and once for the corresponding antithetic run. For the next pair, seed save will be updated with the unused seed for stream 2. In this template, it is assumed that we are only interested in one output result. As a result, we define one persistent save value that is named a save value standard, which is initialized with the value 0. The purpose of this save value is to store the result of the non-antithetic or standard run. We will need this to average it with the result of the antithetic run. In general, we also need to define some useful variables to produce the desired results of the simulation. In this example, we define the variable a var with some expression that produces the desired result. We then define a useful persistent collector to save data across replications. We also define the variable ci half-width, which stands for confidence interval half-width, with the function confidence, so that we estimate the half-width of the confidence interval about the average of the desired result. Then we have print statements that print the headers of the desired output table. After that, we start the replications. These replications are performed by a while loop whose argument is end replications. The while loop contains two sets of statements, one in green and one in purple, that show the standard run in green and the antithetic run in purple. In the standard run, we start by using the statement antithetics 0, which turns off antithetic sampling in Stroboscope. We then seed all, which seeds all the streams using seed save, which is the save value into which we save the original seed. Then we have the statement clear that clears the simulation of all resources and all non-persistent statistics, including save values and collectors. After that, we initialize the queues as appropriate. The simulate until statement runs the simulation until sim time exceeds some sim time limit. And finally, we save the desired result of simulation into the save value a save value standard using the variable a var. This is the crucial step because this is the value that we will average with the result from the antithetic run. At this point, we have run the model once using the standard run. Now we're about to run the model for the second time, and the second run will be the antithetic run. To do that, we use the statement antithetics 1, which turns on antithetic sampling in Stroboscope. The statements that follow, seed all, clear, init, and simulate until, are exactly the same as for the standard run. At this point, if we were to evaluate the variable a var, that variable would produce the antithetic metric of interest. This is done in the next statement, which collects into collector A call the average of the two runs that we're interested in. The result from the standard run is stored in save value as save value standard, to which we add the variable a var, which gives us the result from the antithetic run, and then we divide the sum by 2. And that gives us one observation of the average of the standard and antithetic runs. At this point, we have collected one sample. The print statement prints one row of the desired results. This print statement prints 4 numbers. The first number is the number of samples that have been collected into collector A call. In the first run, it will simply be the number 1. After that, we print the result of interest from the standard run, which is saved in the save value as save value standard. After that, we print the variable a var, which gives us the result of interest from the antithetic run. And after that, we have a formula that averages the two and gives us the average of the standard run and the antithetic run. At this point, we have collected the result of interest, and we have also printed the result of interest, so it is time to proceed to the second loop. To do that, we assign to seed save the result of the expression as seed 2, which gives us the integer random number at the very beginning of the second stream, which was never used. This means that the integer random numbers for stream 0 for the next run will come from stream 2 of the previous run, and the integer random numbers for stream 1 in the next run will come from the integer random number stream for stream 3 in the previous run. The next assign statement decreases the number of replications by 1, and when ends the while loop. The while loop will now be repeated, and stream 0 will use the integer random numbers from stream 2, and stream 1 will use the integer random numbers from stream 3 in the previous replication. The remaining print statements print the overall statistics from the collector that show the results of interest, including the confidence interval about the average of the result of interest. The above stroboscope statements produce the following tabular output for 100 replications. As we see, we have a table of results which has 4 columns: the run number, the result from the standard run, the result from the antithetic run, and the average of the standard and antithetic results. This table has 100 rows to correspond with the 100 replications of the model. In the bottom, we have the average and the standard deviation of the pairwise average of results from each run, along with the low and high bounds for the 95% confidence interval. As mentioned earlier, this template can be reused to create new simulation models that use antithetic variates that are controlled by the number of desired replications. This template for multiple replications with antithetic variates is controlled by the desired confidence interval width. It is very similar to the previous model, with the exception of the statements that are underlined. The first underlined statement is the definition of a variable CI width 0.5, which defines the desired interval width. The number 0.5, of course, was chosen as an example. The statements that follow are identical to the previous model until we reach the statement for the while loop. This while loop is controlled by an OR logical expression that has a left side and a right side. The left side allows the while loop to continue for as long as the number of samples that have been collected into collector A collect is less than 3. This is required so that we have enough samples to calculate an estimate of the variance. We need at least 2 samples. The right-hand side is the one that we're really interested in. This logical expression allows the replications to continue as long as the confidence interval hat width times 2 is greater than the desired confidence interval width. The remaining statements of the model are identical to the previous model that is controlled by the number of replications. These stroboscope statements produce the following output for a 95% confidence interval. Again, we have a similar table that has a first column that shows the runs, in this case from 1 to 12, a second column that shows the standard results, a third column with the antithetic results, and a fourth column that averages the standard and the antithetic results in each row. Notice that in this example, we only need 12 replications to achieve the desired width of the confidence interval. The low bound of the 95th confidence interval is 1.8, and the high bound for the confidence interval is 2.3. So the width of the confidence interval is 0.5, which is the desired width. The second variance reduction technique that we will describe is called common random numbers. Common random numbers is the most popular and useful variance reduction technique. It is also known as matched pairs or correlated sampling. As an experimental design technique, CRN is a form of blocking, that is, comparing like with like. The common random numbers technique is useful for the comparison of alternative system configurations. It is an attempt to compare different systems under equal conditions so that any observed differences in performance are due to differences in system configurations and not due to different conditions. To understand what this means, suppose, for example, that we need to determine the difference in project cost between 2 alternative tunneling techniques, A and B. Clearly, the cost of each alternative depends largely on project geology and whether it will prove favorable or unfavorable during construction. For a tunneling project, it makes intuitive sense that a meaningful way to compare construction alternatives is to A. generate a possible geologic profile, B. compute the cost of each alternative for the same geologic profile generated in A, C. calculate the difference in costs computed in B for the same geologic profile in A, and D. repeat steps A to C to collect statistics on the difference in cost. This common sense approach avoids several pitfalls. First, it diminishes the possibility that one alternative appears better than another simply because of chance. For example, because due to pure experimental randomness, it faced more favorable conditions during simulation. For example, given that geologic conditions affect tunneling costs significantly, it is possible for independent simulation runs to lead to the incorrect conclusion that alternative B is less costly than A simply because B's performance was evaluated on more favorable geologic profiles. Also, if the relative cost performance of alternatives is quite close, but the range of possible outcomes is quite large due to external factors, such as the project geologic conditions, independent simulation runs could prove inconclusive and show that A or B is preferred about half the time. When compared under the same conditions using common random numbers, however, it may be that A is always preferred, even if by a little, although the range of possible outcomes of alternative A may still be very large due to the influence of external factors, such as the project geology. This leads to a very important point. Common random numbers does not eliminate a system's inherent randomness or uncertainty. Its objective is to make the inherent system randomness or uncertainty impact each alternative the same way and not favor one alternative purely by chance. Thus, in tunneling, CRN attempts to eliminate the effect of experimental randomness by using the same generated geologic profiles to compute the cost of all alternatives. A concern that remains, of course, is for simulation to generate enough geologic profiles to ensure that the entire range of possible geologic conditions and resulting costs is represented in the results. Also, the fact that common random numbers makes all alternatives face and be evaluated for the exact same geologic conditions makes it possible to gain additional insights that are difficult to obtain otherwise. For example, common random number experiments could show that, given the same geologic profile, good or bad, A is always preferred to B. Or it could show that B is preferred to A only for extremely favorable geologic profiles, whereas A is preferred to B for all other geologic profiles. As a purely statistical variance reduction technique in simulation, the objective of common random numbers is to reduce the number of runs, that is, replications, needed to achieve the required precision in estimating the difference between two or more true means. There are several important points that need to be made here. Common random numbers is aimed at comparing two or more alternative system configurations. This is in contrast to antithetic variates, which is applicable to simulating a single system. Each run in a pair of runs corresponds to a different system configuration. This is very different from antithetic variates, where the system configuration does not change between runs. Common random numbers aims to induce a high positive correlation between the performance outcomes of the two runs in a pair, instead of the high negative correlation in antithetic variates. Common random numbers uses the same random numbers to drive both runs in a pair of runs. That is, it uses positive correlation in the simulation input, expecting that this will carry over and result in positive correlation in the simulation output. That is, if U sub k is uniformly distributed and it's used for a specific purpose in the first run, for example, to generate the ith arrival for alternative A, then U sub k should also be used for the same purpose in the second run, that is, again, to generate the ith arrival time for alternative B. The use of U sub k in the first and the second run must be synchronized. If synchronization is lost, then common random numbers may actually backfire and actually increase rather than reduce the variance. In each pair of runs, common random numbers collect statistics on the difference in performance between two models that may represent a very different system configurations. This is in contrast to antithetic variates, where each pair of runs collects statistics on the average of two values of the same performance measure for a single system. For example, in common random numbers, we might be interested in the performance of a traditional tunneling technique versus the new Austrian tunneling method. These two construction methods are vastly different, and we're interested in their difference in performance. This is very different from antithetic variates, where we would only consider the performance of one of the two, either the traditional tunneling technique or the new Austrian tunneling method. There are several modeling tricks for keeping random numbers synchronized. Again, just like in antithetic variates, the use of dedicated random number streams, using the inverse transfer method of variate generation whenever possible, appropriate wasting of random numbers, pre-generation of random variates, and advancing the streams of random numbers across multiple replications. There are no guarantees ahead of time that common random numbers will indeed work and reduce the variance of the average. A necessary requirement is that the model's response to a particular random number used for a specific purpose be monotonic. An important issue in the implementation of common random numbers is that the simulation models for each alternative system configuration may be different. Implementing common random numbers requires switching simulation models in order to make one run in a pair correspond to the alternative and to make the other run correspond to the other alternative. We shall now present examples of how to do this. The mathematical basis for common random numbers is similar to the mathematical basis for antithetic variates. Again, we shall consider making n pairs of simulation runs that result in the pair of observations xj in the first run and xj in the second run, where xj in the first run is the jth observation from alternative configuration 1 that uses u sub k, and xj2 is the corresponding jth observation from alternative configuration 2, which again uses the same u sub k. Because xj1 and xj2 are observations of two different configurations, they have different expected values and different variances. We wish to estimate u zeta, which is the difference between the true means μ1 and μ2. Let z sub j be the difference between the jth pair of observations for the two system configurations, xj1 minus xj2. The order in which xj1 and xj2 appear doesn't matter. The moments of z are easy to evaluate. The expected value of z is μ1 minus μ2, which is the expected value zeta that we are interested in estimating. Its variance, that is the variance of z sub j, equals the variance of x1 plus the variance of x2 minus 2 times their standard deviations times the correlation coefficient between them. If we make n pairs of simulation runs, then we can take their average that we shall denote with z bar. So z bar is xj1 minus xj2 added up over all values of j and divided by n. The expected value of z bar is easy to evaluate, and it equals zeta, the unknown mean that we're interested in estimating. Because the z sub j are independent and identically distributed, the variance of z bar is again easy to calculate, and it equals 1 over n times the variance of x1 plus the variance of x2 minus 2 times their standard deviations times their correlation coefficient. If instead of performing common random number pairs, we had n pairs of observations, then the variance of z bar would be the sum of the variances of z sub j, which would give us 1 over n times the sum of the variance of x1 plus the variance of x2. We now have two expressions for the variance of z bar. Comparing these two variances shows that the effectiveness of common random numbers depends on rho sub j. If rho sub j is positive, then the variance of z bar is reduced, which is desirable. If rho sub j is 0, then the variance of z bar stays the same. And if rho sub j is negative, then the variance of z bar increases, which is undesirable. So the objective of common random numbers is to induce positive correlation so that rho is actually greater than 0. The examples that follow illustrate how we can do that. We shall now present 4 templates for implementing common random numbers that address different situations that can be encountered in practice. In the first template, the alternatives differ only in the resources used. This is in fact the simplest case. For example, in an earth-moving operation, one alternative could be to use 2 small loaders, and the other alternative could be to use 1 big loader. Switching models in these cases is fairly simple. It only involves initializing queues differently for each configuration. The replication loop in a typical case might look as follows. The first statement defines 4 streams. Notice that the model is supposed to use only streams 0, 1, 2, and 3. The 4th stream will not be used in the model, but will be used to initialize the next replication. Streams 4 is succeeded by the statements that define the model, and then we have the definition of a persistent save value called seed store, where we're going to store the seed for performing the replications, a save value cost with 2 small loaders, which is again persistent, and a collector difference in cost, which is again persistent. The simulation loop is a while loop, which continues as long as the number of samples in difference in cost is less than n replications. So in this case, we're using the number of samples collected in the collector as a counter that we compare to the desired number of replications. Inside the while loop, we have 2 groups of statements. The green statements are for the first alternative that uses small loaders, and the purple statements are for the second alternative that uses a big loader. For the first alternative, we have the statement seed all to initialize all streams, the statement clear to clear the system of all non-persistent statistics and save values and collectors, and then we have the initialization of queues. The underline in it is the statement that really differs between alternatives. In the green set of statements, the first alternative, we initialize loader's weight with 2 small loaders. Then we initialize the hauler's weight with the number of haulers, and we initialize the soil to move with the amount of soil. We then run the simulation with the simulate statement, and at the end of simulation, we assign to cost with 2 small loaders, which is a persistent save value, the result of the variable total cost, which is the result of interest. We're now ready to simulate the second alternative. The set of statements are exactly the same as before, with the exception of the init statement for loader's weight. In this case, loader's weight is initialized with 1 big loader. After simulation, we collect statistics on the difference in cost. So we collect in diff in cost, total cost, which is the result of a variable that produces the desired result, minus cost with two small loaders, which is the save value in which we save the total cost of the first alternative. After that, we assign to seed store the seed for the fourth stream that was not used. This way, stream 0 in the next replication will start where stream 4 was supposed to start in the first replication. Another simple case is when the networks for the models being compared are the same, but some modeling element attributes differ between them. Suppose that in an earth-moving operation with scrapers, the alternatives are to use different queuing disciplines for the scrapers. One case gives a preference to scrapers with high power, and the other gives preference to scrapers with emptier tongues. The replication loop in a typical case might look as follows. These set of stroboscope statements are identical to the previous model, except for the statements that are underlined. Specifically, in the while loop for the simulation of the first alternative, we have the discipline statement that changes the discipline for the queue scrapers to minus pow, which gives preference to scrapers that have larger power. The first alternative is initialized the same way as the second alternative, and then it is simulated until the earth moved is greater or equal than the amount of earth to move. After that, we assign to cost with power discipline the result of the variable total cost. This save value, cost with power discipline, is a persistent save value. Then we have the purple statements for the second alternative. In this set of statements, the discipline statement gives a different discipline to the queue scrapers, where the scrapers with less fuel left are given priority. Again, we simulate this alternative, and at the end we collect into difference in cost, which is a persistent collector, the difference between cost with power discipline, which is a save value, minus total cost, which is a variable that returns the cost for the second alternative. We then assigned to the save value seed store the integer random number seed for the fourth stream that was not used, and we repeat the simulation loops. Clearly, in the above code, the only difference between the two alternatives is the discipline attribute of the scraper's queue. Before running each alternative, the discipline is set to the appropriate expression. The same procedure can be applied to change other modeling element attributes, such as semaphores, durations, and draw untils. The third example considers alternatives that use different data. This is an equally simple case where the difference between alternatives depends exclusively on data. In such cases, instead of setting different attributes, the data is changed between runs. Assume that two different construction methods are evaluated in the model for the construction of a tunnel. In one method, the initial support changes when the geology changes. The cost to change the initial support is obtained by using the current and the next ground classes as indices in a matrix. In the other method, the initial support never changes, and thus the cost is never incurred. The replication loop in a typical case might look like this. We have a streams statement that defines 4 streams. Only streams 0, 1, 2, and 3 will be used in the model. Stream 4 will be used to seed all. There are 3 ground classes in this model, and we have an array that represents the cost to switch the initial support, which is a 3 by 3 matrix. Then come the statements that define the model. These statements should use streams 0, 1, 2, and 3. As mentioned earlier, stream 4 should not be used. We should also have some cost formulas here that refer to the array cost to switch initial support. After that, we have a persistent save value seed store where we're going to store the seed that begins each replication. We also have a persistent save value called cost with the NATM, the New Austrian tunneling method, where we're going to save the cost of that alternative. And then we have the collector, which is persistent diff in cost. After that, we have a while loop that performs the replication. Again, we use as an index the number of samples collected in the collector difference in cost. The first alternative being simulated by the green statements is the adaptive method, which is the New Austrian tunneling method. The first statement, seed all, initializes all the streams using seed store as the initial seed. After that, we have the clear statement that clears the system of statistics and non-persistent collectors and save values. And after that comes the crucial statement, assign cost to switch initial support, where we define the cost of switching initial support for the New Austrian tunneling method as a 3x3 matrix. This matrix for the New Austrian tunneling method actually costs money because the numbers are non-zero. After that, we have the simulate command, followed by an assignment to cost with NATM of the result of the variable cost of tunnel. After that, we have the statements that simulate the conventional method. These are similar to the ones for the adaptive method, and they start with seed all, followed by clear. The difference is that the assign statement to the matrix cost to switch initial support assigns the values 0 for all 9 elements of this matrix. And after that, we simulate the conventional method. Finally, we collect into difference in cost the difference between cost with NATM, which is a save value, and the cost of the tunnel, which is a variable that returns the cost of the tunnel for the conventional method. Finally, we assign to seed store the integer random number corresponding to the beginning of stream 4 to begin the next replication. The most complex case is when the networks for each method are completely different. In such cases, we need to define two separate networks in the same model file. Assume, for example, that two different methods for moving earth are being compared. One method uses pushers and scrapers, while the other uses loaders and trucks. In this case, the skeleton for a common random numbers model file may look as follows. The green statements define the earth-moving operation with scrapers and pushers entirely, including modeling element attributes, but no Q initializations. It is good practice to prefix all the modeling elements with S underscore, such as S underscore load, just in case there is a similarly named element in the network for the other alternative. We then have the purple statements, which define the earth-moving operation with loaders and trucks entirely, including modeling element attributes, but no Q initializations. Again, we prefix all the modeling elements with names with T underscore, such as T underscore load, just in case there is a similarly named element in the network for the other alternative. After we define the networks for the two alternatives, then we have the definition of save values and collectors that will be used to compare the two alternatives. This persistent save value seed store is used for initializing the random number streams for each replication. This persistent save value cost with scrapers is used to save the cost with scrapers alternative to compare it to the cost with trucks and haulers. And the collector difference in cost is again a persistent collector where we save the differences of the results of interest. In the while statement, we have green statements that initialize and run the simulation model for scrapers, and then we have purple statements that initialize and run the simulation model that uses loaders and haulers. The important thing to notice is that when we run the model with scrapers and pushers, we only initialize the queues for the scrapers and the pushers, whereas when we run the model for the loaders and haulers, we only initialize the queues for loaders and haulers. This way, only one network is active in each simulation run. The rest of the statements and the structure of the simulation loop in the while loop is exactly the same as in the previous models. These four alternatives present templates that can actually be used to implement common random numbers in most cases that can be encountered in real life.